In the last lecture, we saw that we have this amazing tool, Embeddings. You provide it with text, it returns you a vector, and all the vectors created with the same embeddings models share some kind of spatial relationship which is akin to the semantic relationship. So we saw that we can find related concepts or know how related some two concepts are, or two strings, maybe a whole document, how related they are semantically, just by analyzing the Euclidean distance or the cosinus difference, the cosinus of the difference of the angle. So that's amazing. But how does it help us? What's the use? How can we use this property? Well, it turns out that since the 1970s, so it's like 50 years ago, we have the technologies in databases invented indexes, which are indexes that allows us to index records in a table according to the embeddings and one dimension of comparison. So if we have, for instance, cosinus similarity, and then we have one set of embeddings, we can index these embeddings, and then we can, with a reliable algorithm, almost instantly, with a really fast response, you provide it with a new embeddings, and will provide you with the nearest objects ordered by the distance, the closest, the first one, and the next one. So this allows us to create what we call an embeddings database, which is a database manager that uses embeddings as the keys for the index. It's not private key because we're not going to find the identity here, but the idea is that we make a query and we get a number. We will call it K, the top K, the number, the K number of closest objects that are to our to the embeddings that we provided. So then we are going to call these tables which are indexed with embeddings and one similarity function. It's important to know that the embedding function is always the same. If you use one model and one vector size, it has to be for all the embeddings in this database. And we are going to call these tables collections. So the simplest possible embeddings database manager will have the following functions. First, we have create collection, which needs to receive a name, an embedding function according to an LLM, which can be a local LLM like Nomic or OpenAI or Mistral or Claude or Gemini or whatever provider or model or open source model that provides embeddings. Then a description, why not? And then what is the metric that we're going to use? We saw that cosinus similarity, Euclidean distance, what is the metric that we're going to use? And now we have the collection. And now in this collection, what we can do is insert into the collection what we call chunks. If we have, for instance, a large document that we want to rack, what we're going to do is break down this document in different chunks by number of characters or number of tokens even, or we will see different ways of chunking. But the idea is that you provide a text like a string, 255, 2000 characters for example, and some metadata. We will talk later about what metadata are we going to do, and then the collection is going to insert the chunk and its metadata, and it's going to return us an OK message or KO. It didn't work if it didn't work, but it's just like that. Insert. This is my chunk, this is my metadata. The collection manager is going to call the embedding function, is going to calculate the embedding for the chunk, is going to put it inside the index, and is going to save the chunk and the metadata. And the metadata is going to be very important for us. And then we just need one more method, the query. So we have the collection, the text of the query, which can be the same text as a chunk, and then the top K, And we can optionally put a threshold. For instance, if we say if something is really divergent of what we are asking, don't return any message. And if we are going to work with thresholds, then we have to tune it. You have to know your embeddings function, you have to know the domain, the type of document that you are embedding, and how similar it is behaving. You have to test and know at what point you want to set the threshold, because the contents are not related. But if you want to be safe, you just forget the threshold, and the query is going to return you a k number of chunks if it has enough. And for each chunk is going to provide you the chunk content, the metadata, and the similarity for each chunk. So, and that's it. That's the simplest possible collection manager, and that is going to go a long way. We can implement this with a lot of technologies, but all of these technologies are about just these three things: create the collection, insert contents in a collection, and then query the collection. And that's it.
In the lecture, the Collections Manager was 3 functions on a slide. Now let's open the file. One Python module, about 100 lines, implemented on ChromaDB, an open-source embeddings database. Everything you saw, create collection, insert, query, is in here. By the end of this walkthrough, you will know what every line does. First, the metrics. The lecture said cosine or Euclidean. Chroma calls these index spaces, cosine and L2. A small dictionary maps our names to chromas, and the comment already warns about a trap we will meet at query time. Chroma's L2 space returns the square of the Euclidean distance, not the distance itself. Every collection needs an embedding function. The default one calls any OpenAI-compatible endpoint, the same interface you have used all through this course. It reads the endpoint, the model, and the key from the environment. Out of the box, that is a local OLAMA running nomic embed text. No key, no cost. And you can pass your own function instead. Anything that takes a list of strings and returns a list of vectors. What does createCollection give you back? A small data class. A handle. It carries the name, the description, the metric, the embedding function, and, behind an underscore, the Chroma collection object itself. That underscore is a promise. Your application talks to the handle, never to Chroma directly. The abstraction layer, in one field name. Now the first function. 2 decisions happen here. If you give a persist path, we build a persistent client. The collection lives on disk, at that folder, and survives restarts. No path, an ephemeral client, memory only. Then, get or create. If the collection already exists, you get it back. That is what makes reopening work. The metric is planted in the collection's metadata as the index space, and the embedding function is attached to the handle. One rule to remember: everything in one collection must be embedded by the same model, or the geometry means nothing. Insert, first half. The chunk must not be empty, and the metadata must carry at least a source. Then, the chunk number. If you did not give one, we look up the chunks already stored for that source and take the next number. Chunk numbers grow per source, automatically, exactly what the lecture promised. Insert, second half. The id is the source, 2 colons, the chunk number, readable, and deterministic. Then a check Chroma will not do for us. If that id already exists, we refuse, and we say so. Chroma's own ad would skip a duplicate silently, a KO pretending to be an OK. Then the real work. Call the embedding function on the chunk and hand Chroma 4 things: the id, the vector, the document, and the metadata. Return OK, or KO with the reason. And query. Embed the question with the same function. That is the whole trick. The question and the chunks live in the same space. Ask Chroma for the nearest results, with documents, metadatas, and distances. Then the translations we promised. In a cosine collection, similarity is 1 minus the distance, and the threshold keeps chunks at or above it. In a Euclidean collection, we take the square root, the true distance, and the threshold keeps chunks at or below it. Each result carries its chunk, its metadata, and its score. Nearest first. And that is the whole manager. About 100 lines, one engine, behind an interface. If one day you need something beefier than Chroma, you rewrite this one file. Your application, and everything you build this week, does not change.
Demo time. In the lecture, I was talking about what a collection, what a RAG database, embeddings database look like, and I defined the collection from three methods. Those three methods were create collection, insert, and query. So here in our repo, we have the collections manager, where it is an easy implementation of a collection using ChromaDB. ChromaDB is a popular open source, low impact collection embeddings database. It uses the same engine and formats as SQLite 3. So SQLite 3 is a good database for most of the cases, and unless you have high scalability problems, it should be enough for you. But what we're going to do here is just stick with the three methods that I provided to you: create collections, insert, query, and then you can implement it with whatever you want. For instance, if you want to scale, you can use, for instance, Postgres SQL, and it has right now an embeddings index, so you can use PostgreSQL normally and have some tables that are indexed with embeddings, and then you have a collection that you can implement. But if you have this abstraction layer, you don't depend on one implementation. And the easiest implementation that's out there, and it's very reliable, is ChromaDB. So I would go with ChromaDB, but let's study these three methods: create collection, insert, and query. Now we have a demo. Here we have a demo, which is again one of my explorers. You look at like a lot explorers. Then we will use a popular embeddings model, which is open source, and you can run it locally with almost no resources, no GPU. You can run it with, for example, with Olama. You just do Olama serve, you pull this model, and then you run the context explorer, the collections explorer. This explorer will have four methods. One is just enter one text. If we enter one text, we will do a query. We can add some text and we can seed. What we will do if we seed is that we will add some content, so we don't have to play a lot, and then we can mix and match. So let's go to the terminal. Okay, no, it's not here. The terminal is here. So just remember, we have to do the UV-venv thing, and we have to do source being activate, etc. Now I'm going to just run the collections explorer, and here we are. So this is the application. If I do /list, it's empty, so I'm going to do seed, and I can do list. I can see that we have some information here. So in the information that we find here in the system, we see that we have two domains. One is about recipes, and one is about the Acme Corporation that we saw in a previous demo. So if I ask, for instance, about cake, I'm going to see that the highest similarity over 0.5 is about the recipes, and it's 2 eggs and a cup of flour, which is quite related to cake. And then we have this information that it's like nonsensical. I don't know what cake is there, but if I, for instance, add croissants with chocolate, and now source okay, now I'm going to list, and now we have recipes 1, recipes 2, and now we have the croissants with chocolate. So if I ask again for cake, we see again that the recipe of 2 eggs and a cup of flour is related to cake, and also croissants with chocolate is somewhat related to cake, but not as much as the actual start of the recipe of that. Then if I ask for weight, I see that the pallet that carries 600 kilos is what is more similar, and then this recipe about a cup of flour, sometimes cups are related to weight in recipes, so it's somewhat related, and also the top speed with this a physics measure is related. And then we have this low similarity of 0.399 about the croissants with chocolate, which is not related to weight. But if we do chocolate now we're talking 0.778, really relevant croissants with chocolate, and the recipes that needs 2 eggs. Now it's a recipe. Maybe we have something to do with chocolate, but here the pallets pushing ships with an emergency stop is not related. So explore. You can put as long as chunks as you want, and you can play with just these 3 methods: insert and query. And if you need, if you want to start all over again, if you remove the contents of the collection store, the files within the collection store directory, you can start all over again, or you can just do the UV run collection explorer, and then you will have an embeddings database which is on memory, and you have to seed it again. But now the database is on memory. Will be faster actually, but you will not have persistence. Okay, in ChromaDB you also can have a collection which is implemented in the memory of the computer, or can be in a persistent file. For usually you will want a persistent file, and of course you can create as many collections as you wish. Take care. Now, if we want to do RAG with our collection, what we have to do first is to put some documents inside our collection. So we will have our documents that for now we will think that we are working with any kind of document, PDF documents, Word documents. I sent you, for instance, the Markdown library. It's a well-maintained library by Microsoft that allows to convert almost any kind of document to Markdown. We can also use OCR models like Mistral OCR or DeepSeek OCR, which locally do very good OCR of documents, and then you can get a Markdown document with all the images and everything. And then we have a nice document, a nice Markdown document that we're going to ingest. What we're going to do is this document is we're going to store it in some part of our system, somewhere that we can access it via web. If our application is a web application, for instance, in FastApp, you're going to store it in a subdirectory of static. This is my document, so you can link it. And then when you say I extracted this chunk from this document, you can click in the document and see if the chunk is there or not. And then what you're going to do is to break down the document according to a chunking strategy. We are going to break the document into chunks: first chunk, second chunk, third chunk. And then each chunk we're going to insert it as we saw when we were describing the collections. Remember, create collections, insert into the collection, query the collection. So you take all the chunks and you add the metadata that you need and you insert it into the collection. So what is a chunk? I've been talking about chunks. What is a chunk? The chunk is the unit of retrieval. You break the documents, you break all the documents that you are going to put inside your collection, but you bring it in a pieces small enough so so it's small enough that you can calculate a relevant embedding, and big enough that you can inject it into a prompt, and it's going to provide you some meaning, so the assistant is able to provide to get some information out of it to provide the user when we do a query. So it's have to be small enough so we can embed it and insert it into a prompt, and big enough, and that means something. So for instance, for me, I like a point between 1,000 and 2,000 characters. I find that it's a really good measure, that you get a lot of information there, and current models can get a lot of meaning from a lot of meanings, and embeddings work well with this 1,000, 2,000 characters. But you have to do your own tests with your domain. So the important thing is that the size of the chunk is not something that you can improvise. You have to test. You have to use tools like the Collections Explorer and insert different sizes of information and see how well it behaves. So I propose to you two plain chunking strategies. One is by size, just number of characters, and we will have like a sliding window along all the document, like taking 2,000 characters, 2,000 characters, 2,000 characters. But this would be a problem because we can get, for instance, phrases broken down in the middle. To avoid that, what we do is we have an overlap, for example, of 100 or 200 characters, and then what it does is that if a phrase is broken down in a chunk, in the next chunk is going to start 200 characters before, and the phrase is going to be intact in the next chunk, so the embedding model can get some semantics out of it. Then you can have, for instance, tokenizers that are going to be aware of the semantics and the phrases and the punctuation signals, and then you can do and then you will not need overlapping, because it's going to stop, especially exactly when a phrase ends or for a punctuation. But sometimes the documents are not well punctured, or they don't make any sense, or simply the analysis fails. Another way is to use Markdown. As you know, the hashtag symbol, it's going to allow us to break the Markdown document into heading 1, heading 2, heading 3 or 4. And then you can say, I'm going to create a chunk out of every heading 2 section, or heading 3, every heading 3 section, and all of subheadings is going to be a chunk. You know your document and you can choose that. It's easy to create a parser that does that, and this is interesting because it's going to respect the author structure. So you choose, you test, you can do your tests, and then you decide what chunking strategy you are going to use in your RAG system. And now, metadata. What metadata are we going to insert? You can insert a lot of information. But for instance, the title of the master document, if one chunk is extracted out of a document, you say this chunk belongs in this document. And you can have, for instance, a URL. If you stored the document in a place where you can link it, then provide the link of the document. Or if you have a distillation in Markdown, then you can provide a link to the Markdown of the distillation. Also, if you are chunking a document, you can say this is the 3rd, the 4th, the 6th, the 100th chunk number. You put the chunk number, and also you would like to, it's interesting for you to put the chunking strategy inside the metadata of the chunk and the date that you ingested it. So you're not going to use it for the RAG itself, but for knowing what you're doing, to profile, to devise. Okay, for instance, you can use a collection and use for the same document 2 chunking strategies, and you can see what chunks are being retrieved or not, and what gives you better results. The only way is to test it in your system and with your documents, and then you will know what to do. Okay, now it comes to the rack. It's really easy. You know already rack, you know how to do it statically. Now what we do is just, instead of retrieving a static document, what we're going to do is take the user input, turn it into the query, and now we query the collection with the top K. Usually 3, it's okay. Then you get the results of the collection, and then you format it in some way. You can provide just all the JSON that the collection provides you, and the LLM will decide what to do with it, or you can format it in a nice markdown, so it's easy for instance, later for you to see what is going on. If you, for instance, do a debug of the text that are going to go into the LLM, then you take this markdown or this JSON, you insert it in the prompt template exactly like you did in single file rack. Here I would like to say one word about frameworks for rack. Don't use them. I had really bad experience with LangChain. We started our project and it was for us really easy to use LangChain, just import a package and do a couple of Python sentences and everything was fine. But then we wanted some control on our prompts and what was going on, and then we found out that LangChain was inserted things in our prompts that it was really difficult for us to access the internal parts of all the retrieval chain. And then LangChain told us, if you want to control this, you have to pay for the premium version. I don't know if they say it's Langsmith or no. Rack is so simple. You don't need frameworks. You just, by using plain Python or really simple libraries, you can control all the rack. So you don't use like Langsmith or LangChain or all of these platforms. They all say that they are open source, but actually they're not. They're trying to lock you in technologically, and if you want to scale or you want to really control your product, then they're going to ask you for money, and they want to lock you in technology, want to lock your product in their framework. Don't do it. And if you really need to do it, investigate all the possible cases where you want to have a fine control of the augmentation chain. For us, it was a lot of time that we lost because we chose the wrong technology, and since then I'm really adamant not to use frameworks for things that I can implement myself. So I prefer to understand what I'm doing, and once you understand what you're doing, you just write the code, write it clearly so you can make all the modifications and you can do interesting things with it. So then the threshold. Be careful with the threshold. You have to test the threshold in the kind of queries that your users may do or may not do. At what point you have to put the threshold so the embeddings collection is not going to return anything. You have to be really careful. If you don't know what you're doing, put it at 0. But if you really want to put the time, do a lot of tests and do the calibration yourself. Okay, so that's it. Dynamic rack is really simple. Just use a collection, use an embeddings model, break down your content into chunks, insert it in the database. The process of getting a document and putting it inside the collection is called ingestion. And after a document is ingested, then you just make queries and that's it. So easy. We are almost there. Now, in our repo, I have here one demo, which is one of the Explorer demos, which implements a small chat using embeddings for rack, so a dynamic rack. We also have here a simple dynamic rack, which is a full-fledged rack software that you can test and see the code and see how a full rack software works. But here in the demos, we're going to see the Explorer so we can see how it works step by step and how the context is being built as we have been doing. So we will have one document, which is the knowledge. It has information about one of this fictional company, and also we have the environment example where we can put our model, the endpoint, our API key, and we can also play with the chunk sizes and overlaps, and even you can modify the context fields, the knowledge file, so you can work in another way. In this case, the Embeddings Explorer is ready to go, and let's go to my terminal. In my terminal, let's see, we have our document, and this is my environment. I'm going to use Ministral in my local machine. I'm going to use Nomic for embeddings. This is the OpenAI endpoint, and this is the knowledge. This is the knowledge, so we have a lot of information. I made it a little bit bigger. I still think that the repo is not committed, so I'm going to just remember that we have to do the UV, venv, and then activate the things. My environment is already in the right UV environment, so I'm going to just launch the Embeddings Rack Explorer. UV run Embeddings Rack Explorer. So the system tells me that has ingested 15 chunks from knowledge text with a size of 320. I already told you that my chunk size is around 1,000, 2,000 characters for a nice chunk of information there. But this is a demo, so we can do one of the questions that it's proposing. So let's paste it here. How quick is the delivery to reward? And now let's see how this is working. So first of all, this is the question, and now the system did a retrieval. So it did a similarity search, and Bile robot that ferries pallets between shelving and lock. Okay, we have this information, and what is going to be sent to the LLM is this context. We have filled the prompt template, and that's it. And the answer says that the pallet pub has a top speed of 24 meters per second. Let's ask and we ask another question, and we see that now we do another search, and this is the similarity search that we do. So we inject everything here because everything is above the similarity threshold, and now this is the context. And look, how quick is the delivery robot? The pallet pub has a top speed of 2.4 meters per second. All the injection that we did in the first message has disappeared. The model has forgotten it. And you can see that in the system prompt is answer using only the context. If it's not here, you don't know. Okay, so now the only thing that the system knows is what has been retrieved in this instance. So this can provide you with a hint of how these systems can be improved in the future. So this is how a RAG system works, and this is what everybody knew about RAG by 2003. It's just we have an embeddings database, we put some chunks, we do a similarity search, we have a prompt template, and we build the context one by one. Now you have some exercises to do. You have a small project, so you build this, and this is a fine RAG system. In the next set of lectures, I don't know if we're structuring by weeks or by sections or by chapters as of now. In the next week, we're going to see the problems that we find when we bring these rack systems into production. We will see the limits, but as cool and interesting and magical embeddings are and these systems are, what are the problems of embeddings and what are the problems of dynamical rack when we put it in production, and what solutions can we provide. And this is not going to be, our answers are not going to be based on hype or trying to sell you some technology or framework or product, by simply looking at the problems, looking at the technology, and finding simple and effective solutions to do what the course promises, which is to bring these things to production.